Picture a world where the impossible becomes reality, where the boundaries between science fiction and scientific fact blur into a fascinating new frontier. Today, we're exploring a breakthrough that seems to defy our understanding of physics itself: quantum teleportation. While we're not yet beaming humans across space like in Star Trek, scientists have achieved something equally extraordinary: the ability to instantly transfer the exact quantum state of one particle to another, regardless of the distance between them. The concept might sound like it belongs in a science fiction novel, but this is very real, cutting-edge physics happening in laboratories around the world. At its heart lies one of the most mysterious phenomena in quantum mechanics: entanglement. Imagine two particles so intimately connected that their quantum properties remain linked no matter how far apart they are. Einstein famously called this spooky action at a distance, and it serves as the foundation for quantum teleportation. The process unfolds like an intricate quantum dance. It begins with two scientists, let's call them Alice and Bob, who share a pair of entangled particles. Think of these particles as twins, who always know what the other is doing, instantaneously, across any distance. Alice has one particle, and Bob has the other. When Alice wants to teleport quantum information to Bob, she introduces a third particle containing the quantum state she wishes to transfer. Through a precise measurement technique, Alice creates an interaction between her entangled particle and this third particle. This is where the true magic of quantum mechanics reveals itself. The mere act of measurement causes the original quantum state to vanish from Alice's particle, like invisible ink disappearing from a page. But it doesn't simply disappear. It reappears in Bob's particle, provided he knows how to decode it. Alice must send Bob the results of her measurement through conventional communication channels, and upon receiving this information, Bob performs specific operations on his particle. Through this process, Bob's particle transforms into an exact replica of the original quantum state Alice wanted to transfer. This isn't just theoretical physics. It's been demonstrated in real laboratories. In 2004, researchers at the University of Innsbruck achieved a remarkable breakthrough. They successfully teleported quantum states between calcium ions, separated by several micrometers. While this might seem like a tiny distance, the implications were enormous. The team verified that the quantum state vanished from one ion and materialized in another without ever existing in the space between them. This experiment marked a crucial milestone in quantum information science. The applications of quantum teleportation extend far beyond laboratory curiosities. Scientists and engineers are working to harness this phenomenon to create quantum networks, the foundation of what many call the future quantum internet. Unlike our current internet, which is vulnerable to hacking and interception, quantum networks promise unprecedented security. The very laws of quantum mechanics make it impossible to intercept or copy quantum information without detection, leading to truly unhackable communication systems. But this revolutionary technology also presents unique challenges and raises important questions about the nature of information itself. How do we regulate something that seems to defy classical physics? As quantum teleportation moves from laboratory experiments to practical applications, policymakers and scientists must grapple with new regulatory frameworks that balance innovation with security concerns. The tension between theoretical possibilities and practical implementation remains a central challenge. While quantum teleportation works perfectly in carefully controlled laboratory conditions, scaling it up for real-world applications requires overcoming significant technical hurdles. Scientists must maintain the delicate quantum states against environmental interference, develop more reliable quantum memory systems, and create networks capable of distributing entanglement across greater distances. As we stand at the threshold of this quantum revolution, The implications stretch far beyond the realm of physics. Quantum teleportation challenges our fundamental understanding of information, transfer, and storage. It suggests that information might have more in common with identity than we previously thought, capable of disappearing from one location and reappearing in another, perfect and unchanged. While we won't be stepping into teleportation chambers anytime soon, quantum teleportation is already revolutionizing our approach to information security and computing. As research continues and technology advances, we're moving closer to a world where quantum networks form the backbone of ultra-secure communication systems, and powerful quantum computers exchange information through teleportation. The story of quantum teleportation reminds us that the line between science fiction and reality is often thinner than we imagine. What seems impossible today might become commonplace tomorrow, driven by human ingenuity and our deepening understanding of the quantum realm. As we continue to unlock the mysteries of quantum mechanics, we're not just advancing technology, we're redefining the very nature of information and identity in our universe.